Okay, in this video I want to show you how you can represent waves with wave fronts and with rays. These are equivalent ways of representing waves. Often we use one method for one thing and another method for another thing, but they're actually interchangeable. So often we'll use rays with light, because that's a common way to think about it. But if we were drawing the waves we saw in a ripple tank, we would probably use wave fronts. But the two methods are actually interchangeable. So I want to show you how you can interchange them and how they are the same thing. So these are ways to represent any waves, just to be absolutely clear on what's going on here. Okay, wave fronts look a bit like this. This is a simulation of a ripple tank. Hopefully you've seen a ripple tank where there's a thin tray of water, and you've got a dibber that dibs up and down. Either it's a straight line dibber like this, or you can have little circular or spherical ball-shaped dibbers that make different shape waves. But basically, ripples pass along the surface of the water, and then these cast shadows. They project little bright and dark lines onto the table below. You might be interested as to how water can cast a shadow, given that it's clear. You might want to think about that. Anyway, these are wave fronts. What you're seeing here, these bright and dark things, are what we would call wave fronts, just so you know what they're looking like. And that's how they move. Well, maybe you've used a ray box at school. Okay, it's a box that you plug into a power supply, and out of that you get a ray of light. Whoops, not particularly straight. There we go. And if you were to direct that through a glass block, maybe the ray would do something like that. I don't know. Okay, so these are two different ways you've seen waves. Light you can think of as a wave. We see it often as rays if we use a ray box, but then water ripples are waves, and we see them doing this. What's the connection? Well, I'm going to represent the same thing using wave fronts and with rays, and we'll start with this because it's simple. Okay, so let's say we've got our tank of water. This thing here is the dibber. Okay, so it's a bar, and it's moving up and down. So it's moving up and down, in and out of the screen as you can see it, and the water is in the plane of the screen. What you're going to see is ripples like this. Ripple, 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 and so on. Now the distance, by the way, the distance between each of these ripples is one wavelength. It's the distance from one peak to another peak. Okay, so that's one wavelength, and these ripples are going to be moving to the right along the water. These are wave fronts. Now we could equally show the same thing using rays, and the ray representation, which you might think is weird to use, would look like this. The rays are showing the direction of motion of the waves. That's what they're doing. They're arrows showing the direction the wave is moving. Okay, so all across this the wave is moving to the right. So the red things are a ray representation, they're rays. The blue things are wave fronts. Take a look at them. Is there anything you can notice? Maybe there is. Okay, let's move on. Here's another situation in the ripple tank. Let's get the ripple tank, and we'll go for a single source. This is now when you've got one of those ball-shaped dibbers, and it's just dibbing up and down in the middle of the ripple tank, making these ripples that spread out in all directions. Remember, what we're seeing here are peaks and troughs in the water ripples. Okay, these are the bright and dark things are peaks and troughs. So these are wave fronts, and again, the wavefront representation of a single source of waves. What colour did I do wavefronts in? Blue, I believe. Let's do the source of waves in green or something. So that's the dibber that's going up and down. What you can see are wave fronts spreading out. Concentric circles. Once again, the distance between any two of these wave fronts is the wavelength. Okay. Now, what's the same situation? So I didn't really say anything about it previously here. You know, why was I using these rays? But we can think about a situation like this with light. A single source of light. So this is a single source of water ripples going in all directions. Well, a single source of light going in all directions, we would probably represent with rays, because we're familiar with using rays for light. For light, we'd say, well, there's rays of light going in all directions. Here they go. Rays of light spreading out in all directions, coming from this light bulb or whatever it is. Now I'm saying to you that these are both equivalent ways of expressing the same thing. Okay, so waves spreading out from a point, you could express with rays, which indicate the direction the waves are moving, or you could express with wave fronts, which are linking peaks of the wave. Okay, they're both ways of expressing the same thing. Now, by this stage, you might be noticing something about the wave fronts and the rays. Okay, so again, whoops, the rays are in red, the wave fronts are in blue. Same over here, rays in red, wave fronts in blue. You might be noticing that they're at right angles to each other. Okay, so everywhere you look, wherever a ray crosses a wave front, you'll see that it crosses it at 90 degrees. Have a look on this diagram here. Everywhere where a ray crosses a wave front, whoops, that's at 90 degrees. Same here. Anywhere where a ray crosses a wave front, it's at 90 degrees. So that's like one of the key things, which if you're making notes, I'd write that down. Okay, so wave fronts are always perpendicular, are always perpendicular to rays. Full stop. Okay. Now we can extend this approach to then start thinking about all sorts of other stuff. Now I don't want to go through an exhaustive list of all the different things here, because it's good for you to think about them yourself. So maybe I'll just do one. Let's do diffraction. Now you've probably seen diffraction with a ripple tank. You might have seen diffraction with light. Okay, with a ripple tank I can make diffraction happen here. If we go back to our, where's it gone? If we go back to these waves here, okay, if I want them to diffract, I'm going to make them go through an obstacle. Okay, so yep, here we go. So I'm going to start drawing an obstacle in here, and you'll see that the waves are going to respond to that. So I've made an obstacle, and the waves are passing through the middle of that gap, and you'll notice that the waves diffract. They spread out when they go through the gap. Now I'm going to represent this with wave fronts, because that's what we're looking at. I'm also going to do it sideways, just because that's the way I always do it. So if I've got a gap and some wave fronts coming in, I'm going to try to keep the spacing between them consistent, because the spacing between them is a wavelength. Then I think it looks something like, I can't remember exactly how much of it's spreading out, maybe something like this. Okay, it's spreading out quite a lot. So notice I'm trying to keep my distance between my wave fronts the same, consistent here and here and here and everywhere. Okay. Now, how do you represent that with rays? Well, remember the rays are always perpendicular to the wave fronts. So if I start doing a ray here, it's got to go across that at 90 degrees. It's got to go across that at 90 degrees, and that, and that, and that, and that, and that. Easy. Okay. Now, if I do another ray up here, in order to keep going across at 90 degrees, the ray has to bend a bit, okay, so that it keeps, and even then I haven't quite bent it enough actually, so it keeps crossing at 90 degrees. So in the wavefront representation we see these blue wavefronts going through the gap and spreading out. If we were to represent it with rays, then the rays start off parallel to each other on the left hand side of the screen here, moving along. When they go through the gap and diffract, the waves diverge a bit and they end up spreading out. And this is exactly what happens with light, which is what we usually represent with rays. So if you've seen light go through, if you've seen like laser light, if your teacher's demonstrated like I have laser light going through a thin slit, okay, you have like a laser beam here shining onto a slit, you'll know that when it gets to the other side of the room, okay, it's spread out. So the light that's gone through here, whoops, wrong colour, the light that's gone through here hasn't just gone straight on like this, it's spread out a bit. Okay, you have to get quite far away to notice that it's spread out. So the screen would have been, the screen that the laser light went onto would have been quite far away, a good few meters away. But you'll notice that that laser light has spread out. Now obviously that's not the way we represent it with scribbles and stuff like that. No, we represent light often with rays. Now those rays, when they go through the slit, the gap, bend slightly, change direction, okay? And if we were to represent it with wave fronts, the wave fronts here, they would actually be much closer together than this, by the way. Even closer together than this. The wave fronts here start off as totally straight lines, and then here they'd be ever so slightly curved. But because the amount of diffraction is so small here, the curvature would be very hard to notice. So wave fronts and rays, you can use them both to represent the same thing. Okay, so what you need to be able to do is represent loads of processes with either wave fronts or rays. So if I were to say to you, what about reflection of light at a mirror? Okay, and if I were to send in 3 rays, you'd be totally fine. You'd be like, okay, well, put in some normals. Whoops, this one doesn't go all the way. When light reflects, the angle of incidence equals the angle of reflection. So these are going to reflect off probably something like this. All well and good, we're familiar. But if I then said, okay, represent that with wave fronts coming in, I'm just going to do them in between, what would happen? Well, I'll leave you to think about that. Likewise, if you were to do refraction, let's say this is some glass and we had some light rays coming in, you know what's going to happen. They're going to refract towards the normal. Familiar. What about if I said represent that with wavefronts? So this is something to think about, okay, what's going to happen here, and you need to be able to draw these diagrams reasonably accurately. So in the lesson we'll look at representing reflection and refraction with wavefronts and see what the diagrams look like. Right, hopefully that's a brief introduction anyway to wavefronts and rays. Remember, wavefronts are always perpendicular to rays. So if you know what the wavefronts are doing, you can work out what the rays are doing. Conversely, if you know what the rays are doing, you can work out what the wavefronts are doing.